Good day to all of our petroleum industry colleagues. I hope everyone is safe and sound. My name is Luma Almana. I am a petroleum engineer currently working with Halliburton, Iraq as a field engineer MLWD. On behalf of Arab Oil and Gas Academy, I would like to welcome you all to our virtual Q&A session for the pre-given course Reservoir Characterizations, Clastics and Carbonates, given by the remarkable speaker Dr. Moustafa Oraby. Dr. Moustafa has 25 years of experience in the industry. He got his bachelor and master's degree from Alexandria University. He holds his PhD from North Carolina State University. He worked as an assistant lecturer at Alexandria University before he got his master's degree. He also used to teach at community college in the United States. Industry-wise, he held many positions in all aspects of the petroleum industry and located in different countries.
Hello everyone, I hope all of you are doing great and staying safe. My name is Selma Rashidi. I'm a petroleum engineer. I owned my bachelor's degree from the American University of Ras Al Khaimah. As mentioned before, our lecture today will be delivered by the Master of Simplifying the Petroleum Technical Knowledge, and our lecture today will be delivered by Dr. Moustafa Oraby, and the lecture will be divided into two parts. The first part is addressing the major questions, which are porosity in gas-bearing reservoirs, identification of salt and anhydrite beds from logs, and multi-well variogram processing.
Hi everyone, good morning, good afternoon, and good evening. My name is Asma Shadi. I'm a petroleum engineer who recently graduated from American University of Ras Al Khaimah. Before we start, I would like to remind you that if it's the Q&A session, so please, if you have any extra questions, please drop them in the Q&A box. So please pay attention and welcome Dr. Moustafa. Dr. Moustafa, the mic is yours.
Thank you very much. Thank you, Luma, Salma, and Asma. As you got heard here, we have actually the Q&A sessions, and it's divided into two major parts. The first one is the one addressing the questions that I used to receive from you through discussion, sending emails to me, and also putting these questions in some of the panels. I will address these questions. The variogram was actually asked by so many of you, so I'm going to spend some time on talking about the variogram processing and how is it different from the histogram that we discussed before. We touched base before on the variogram, and we said the variogram processing is more difficult and it takes into consideration other things that the histogram doesn't. At the same time, there was other questions regarding the porosity and the gas-bearing reservoirs. How the gas would affect the porosity, how the log will look like, especially on the separation between some of the logs. Also, through the carbonate session, we always face the anhydrite beds and the salt beds. How can we identify those from logs very quickly? So we'll discuss these three major questions that I used to receive from multiple of you guys. The second part, as Asma actually said, we'll also give some time for other questions that may relate to the subject or anything that comes to your mind related to the reservoir characterization. Just to don't ask you to be discreet, and don't make it generic questions, because I received some generic questions that requires actually more than one or two or maybe three lectures to address these questions. I understand that you guys like to get more information about things, but sometimes the time limit will put us in a very limited position to answer your questions. Okay, so let me start with the an overview of what we decided to do in this course. We had actually 4 lectures before, and today will be the lecture that we discuss some of the questions that came to your mind. Okay, so for the first question, porosity evaluation in gas reservoirs. To answer that question, actually, I need to make a very quick review on some of the webinars that we discussed already before, especially the webinar that we discussed through the formation evaluation course that was in the summer when we started doing the training, and also on the second lecture in the characterization. Just a very quick review to remind you of some of the characteristics of some of the logs, and how these characteristics will be changed due to the gas existence in the reservoir. Actually, when I talk about gas, this you may differentiate between gas-bearing reservoir, which means gas reservoirs, or gas actually that comes also in the reservoir after being produced, because everybody know that we have something called the bubble point. Bubble point is a pressure point where if your reservoir is an oil reservoir, for example, and you started producing it, the pressure will decrease. Then there is a certain pressure for the bubble points when the gas starts to build up. So in this case, we'll be having three phases: the water and the gas and oil and the gas. Okay. So also some of the wells that you drill or you evaluate after your reservoir reaches pressure below the bubble point, you will also see these type of effects. Okay. So the existence of gas will have some, I can say, signatures on the logs that will help you out identify the process. Okay. So first of all, the composition of fluids in pores in general, we touched base on this before, and we said actually if you look at any reservoir, in the pores that we are interested in, what we find two major fluids: water and oil and gas, okay? Or both actually. So it can be water, oil, and gas at the same time. When we look at the water composition versus the hydrocarbon composition, water is H2O, and hydrocarbon is hydrocarbon. So it's actually hydrogen and carbon. Water is hydrogen and oxygen. So actually, this is a very important thing we found out from just looking at the chemical composition of these fluids, that the water has hydrogen, oil and gas, they also have hydrogen. And the Neutron tool took advantage of this. The advantage is that these fluids, all these fluids, they have hydrogen in it, regardless what the fluid is. The original water that was there before the migration of the hydrocarbon, and then the hydrocarbons, they all have hydrogen. So the people took advantage of having hydrogen in all the fluids components, and they decided to design a tool that actually measures the hydrogen component, and then they will relate the hydrogen to the porosity where the hydrocarbon and the water live in. Okay, so that was the basic idea that we discussed it in details in the formation evaluation. Also, we touched base on this on the second webinar of the characterization. So hydrogen is the component that's shared between all the fluids that we have in a reservoir. So if you measure hydrogen atoms, this can be translated to porosity, and that's all the whole thing about the neutron tool. Okay. So if I look at the neutron tool, it's mainly a neutron source, and this neutron source emits a high energy neutrons, which go into the formation and started to do some collisions with all the particles in there, or all the atoms in there. Let's put it that way. With the collision of all the atoms, they lose energy. And we found out that the one that has the most effective collision on the neutrons is the hydrogen. A single collision can actually cause the neutron to lose all its energy. The only atom that can do this is the hydrogen. So hydrogen is the most effective of slowing down the neutrons from being high energy neutrons to low energy neutrons. So we took this criteria and we designed this tool accordingly. So you send the neutrons all the way, they actually make all collision, and I can see it emits a very high energy neutron, and then all neutron collides with hydrogen and other elements, but the most effective element is the hydrogen. The reason is its mass is very close to the neutron mass, and then hence they have the same mass, then they'll be very effective in slowing down the neutrons. Then we put actually two detectors, near detector and a far detector. And we actually looked at why we have two detectors. That's a compensation for the whole board. And also that was discussed in the formation evaluation webinar. So actually, if we need to get into more depth in why we're having this design, why we're having these two detectors, as I said, it's actually covered in the previous webinars. Okay, so the neutrons come out, they make collisions with all these atoms, and then slows down, and then go to a near detector and far detector. We take a ratio between the near detector counts and the far detector counts. And from this ratio, we translate it to porosity. But the most important part is, and that's what we really need to pay attention to, if you have less hydrogen, you have low porosity. Okay, just pay attention to this. If you have less hydrogen, then you have low porosity. And if you have more hydrogen, then you have high porosity. Okay, so that's how the tool actually translates the counts into porosity. And if you have very low number of hydrogen, then you don't have much of porosity because the hydrogen lives in the pores. Okay, so less hydrogen means low porosity, more hydrogen means high porosity. Keep this in mind because this is very, very critical. Also, I hear you can highlight these two things. Again, I'm repeating myself more and more. Less hydrogen means low porosity. Okay, just keep this in mind. Now, let's assume that I'm having a structure that we also covered in the second webinar in the characterization, where I have multiple layers here of different lithology. We have clay, we have sand, lime, and dolomite. Okay, and this is the structure that contains the majority of the lithology that we deal with, and the majority of the reservoir that we deal with. We actually face clay beds, then we have sand or sandstone reservoirs, and we have carbonate, either being a limestone carbonate or a dolomite carbonate. Okay? Now, let's assume that my reservoir has a 20 PU. Well, this one has 20 PU, and this one has 20 PU, and this one has 20 PU. When we actually looked at how the neutron tool will react to this, and how the gamma ray tool will react to this. Well, the gamma ray, first of all, it will see the clay, and clay has a property of having high gamma ray measurement. So the gamma ray will read high in front of the clay. But since the sand, lime, and dolomite are reservoirs, reservoirs has a characteristic of having low gamma ray. Okay, why? Because it doesn't have much of clay as the clay beds. If your reservoir has very high clay content, that's a bad reservoir. Okay, why? Because the clay will live in the pores, and then your effective porosity will be very low. Also, we talked about the effective porosity previously, and the effective porosity is what we call clay-corrected porosity. So you can have 20 PU, but if clays live in the 20 PU, it can reduce it to 5 PU. Then you lost your porosity. Okay? So the assumption is that what the reservoirs that we have here are clean reservoirs, and they don't have much of clays. Okay. So in this case, here is my 20. How the neutron tool will act to this, and how the gamma ray tool will act to this. First of all, if I am in an oil reservoir, and keep this in mind, if I am in an oil reservoir, we discussed this in the previous webinar. Here is my gamma ray. Gamma ray will read high in front of my clay, and it will read low in front of my reservoir. Okay, this low means doesn't have to be that much low. Low means slower than the clay, to put it that way. So it's slower than the clay because it's not a clay bed, it's a reservoir. For the neutron tool, and since the API asked us to put this on a limestone scale, and that's why you have this one from -15 to 45, we talked about this so many times, then we found that the clay will read very high porosity. The reason is all clays, they have hydrogen in their composition. And since the neutron tool reacts to how much hydrogen do you have, then I will have actually a high reading in front of the clay. Is this real porosity? No, because we know that clays are not really a reservoir and doesn't have porosity that the hydrocarbon can live in. Okay? So in this case, we will see high porosity, but we know that the high porosity is not real. Yeah, but it's only coming because clays, they have a lot of hydrogen in there. So that actually reflects how the neutron tool reacts. The neutron tool reacts mainly to the hydrogen component in anything. In clay, we have hydrogen component, then the clay will read high porosity. In the reservoir, we have hydrogen components coming from water and coming from hydrocarbon. So it will also give us some good porosity. So in this case, we'll see the first thing in front of the clay, we'll see the neutron will read high porosity. Okay? High porosity is in the order of, in the left side of the 20, because it will be higher porosity. Now, when we put the sandstone on a limestone scale, we found that the sandstone will read lower porosity than 20 because we're putting sand on the limestone scale. Again, we discussed this in details in the second webinar in the characterization. Please go back and review this. We discussed it in details there. So in the sand, in front of the sand, you will see that the neutron tool will read less. Actually, it will read 16.5 if it's 20 PU. Okay, so it will read 16.5 since you put sandstone on limestone scale. We always say wrong lithology on wrong scale, it will give you a deviation from reality. Since the sandstone is the wrong lithology on the wrong scale, the scale is limestone. So putting sandstone on limestone, then your porosity will get affected. So the sand will read about 16.5 pu in this zone. While in the second one, which is a limestone, now limestone on limestone, so it's the right porosity on the right scale. So there is no need for any differences. So on the limestone only, you will see the neutron tool will read exactly 20 because the right lithology on the right scale. The lithology is limestone and the scale is limestone. So it will read exactly 20 pu. Okay, there is no reason not to read different. When you go to the dolomite, it's another different, or we call it the wrong lithology on the wrong scale. It's a dolomite on a limestone. Okay, so in this case, you will see it will read higher porosity than the 20, it will be 27.5. So in front of the sand, it reads lower. Okay, so the sand on the limestone scale, it will read lower. The lime on the limestone scale will read exact. Dolomite on the limestone scale will read higher. Okay, right? Then we started looking at the density, how the density will react to this. Okay, so just pay attention to this as well. Now, if I am in a gas reservoir, what's the difference between the gas reservoir in this case and the oil reservoir? The number of hydrogen atoms in gas is less than the number of hydrogen atoms in oil, and the number of atoms in water. So gas will have less number of hydrogen than oil and than water. Okay, so what do you expect in this case? The reason is less hydrogen, it will give me lower porosity. We agreed on this. If I have less hydrogen, I will get low porosity. So this means the neutron tool will read lower porosity in gas reservoirs. The reason is very simple. Gas, they have low number of hydrogen component compared to oil and water. So in gas reservoir, expect your neutron tool will read very low porosity. Okay, so just keep this in mind from the understanding of how the tool works. The tool works on measuring number of hydrogen. Since the hydrogen in the gas is less than the hydrogen in the water and the hydrogen in the oil, then in this case, the porosity in the neutron porosity in any gas reservoir, it will read low. So this means neutron log in gas reservoir, what will be the behavior? First of all, this one, the clay will stay the same because gas is not going to live in the clay. Gas will live in my reservoir, okay? So gas is not going to be in the clay, so the clay will never change. It will be the same, okay? How about the sand? We said if the sand has gas in it, that even low porosity will be even much lower. So you're expecting it will read much lower porosity than even the original one. The original one was low because it was sand on limestone scale. Now, if there is gas in the sand, and since gas has much lower density, much lower hydrogen than the neutron and than the oil and the water, then it will read lower than oil and water. Okay. Again, for the limestone scale, it will be the same. If my lime 20 pu don't have oil or water, it has gas in it, then it will read lower porosity. So this one will be less than the 16.5 that we had originally. This one will be less than 20. So what the gas will do to your limestone in this case, if my limestone 20 pu now is charged with gas, not with water or oil, it will read less porosity. So gas will actually make the neutron tool read less porosity than it should. And the reason is gas has less hydrogen component compared to water and oil. Similarly, in the dolomite, it will read less. Since this is the high side of the neutron, so reading less, it will come up at this point. So it will be reading less than it should. So that's the effect of the gas on my neutron tool. Why I see less porosity than normal? Because gas has less hydrogen component compared to oil and water. And since the neutron tool reacts to the hydrogen component in your rod, then it will be very highly affected. So I see even lower porosity than the normal sand on limestone, lower porosity on the limestone formation, and lower porosity in the dolomite formation as well. Okay, so that's the first thing. First thing is my neutron tool will read lower porosity than it should, and if my reservoir has gas in it. Okay, the reason is gas has less hydrogen compared to both water and oil. All right. Now, let's just go to the density because we always combine neutron and density on the same track. So how the density will react to this? Well, if you look at this, it measures also bulk density. So the density tool measures bulk density. Now, the question is, bulk density is used to calculate density porosity. That's what we do. We take the bulk density and we calculate density porosity. How do we calculate density porosity? Density porosity is rho matrix minus rho bulk divided by rho matrix minus rho fluid. Since we put the neutron and the density on the same scale, and we discussed this in details before, then I have no choice about the rho matrix. Okay, we put both of them on the same scale, on the same track. The scale of the line of the neutron is limestone scale. Then I have to use the limestone density for the density porosity. Okay, to be consistent, because the neutron and the density are plotted on the same track. Okay, if they are plotted on the same track, then they have to be consistent in the scale. Since the API is asking us to put these logs on limestone scale, since the neutron includes rho matrix, then the density porosity includes rho matrix, then I have to put the rho matrix as the density of the limestone. Then my VD will be 2.71 divided by rho matrix is also 2.71. About the rho fluid? The rho fluid is the calibration fluid. The calibration fluid is the water, then the density of the water is 1. So the density porosity will be 2.71 minus rho bulk divided by 2.71 minus 1. If I go there and I see how the density will react in the oil, okay, then if I look at the density of the 20 PU, density of the 20 PU is 2.32. The density of the 20 PU limestone is, okay, hold on a second. The density of the 20 PU sandstone is 2.32. Now let's use the density here and calculate the density porosity of the sand. Okay, density porosity is Pd, rho matrix minus rho bulk divided by rho fluid minus 1, which is 2.71 minus 1. And in this case, if I put this, it will give me a porosity of 22.2. 22.2 is higher than 20. 22.2 is higher than 20. So where is the density porosity will be? Here is my 20. So then density porosity will be on the other side. And that's why when you draw the density porosity, you see certain type of separation. Density to the left, neutron to the right. That separation, we call it the sandstone separation. We are in an oil reservoir, okay? Now, what is the density of the limestone? 2.368. So I go for the density porosity here, it will be rho matrix, which is 2.71, minus rho bulk, which is 2.368, divided by rho matrix, 2.71 minus rho fluid, which is 1. If I do this calculation, I will get exactly 20. Why? Because it is limestone on limestone scale. Limestone on limestone scale, there is no reason to be different. So it will be reading exactly 20. So the neutron and the density will overlay only in front of the limestone. The reason is I'm using the limestone scale. And limestone is limestone lithology on limestone scale. There is no need for any differences. Now, if I go to the dolomite, 20% dolomite is 2.496 gram per cc. If I take this and you plug it into the density equation, or density porosity equation, then your porosity will be 12.5. 12.5 is less than 20. Okay, so then you will be seeing the density is actually going on the other direction. So we say that in front of the sand, I see the neutron density will separate, where density is to the left, neutron to the right. In front of the lime, they will overlay because it's a limestone on limestone. In front of the dolomite, they will separate but opposite to the sand, where my neutron is to the left, my density is to the right. Now, it is actually the same kind of separation with the clay. Now, how can I differentiate between the clay and the dolomite? We said in front of clay, I have to see the gamma ray reading high. So when I see this separation, that the neutron to left, density to the right, then in this case, I have to check with my gamma ray. If my gamma ray is high, I will call it clay. If my gamma ray is low, I will call it dolomite. So the dolomite and the clay, they share the same type of separation, but the judge Is it clay or is it dolomite? The gamma ray will do that for me. Okay. So this is how the neutron density will react in front of, in the case of oil reservoirs. Now, how about the gas on the density? Well, density of gas is less than density of oil and density of water. So this will make that the bulk will be actually, if the bulk was 2.32 in the case of oil, then it will be less because it's now full of gas. And also the density of 2.368, it will be less because my limestone is full of gas. And the 2.496, my density will be less because my reservoir now is full of gas. So the gas will make my density less. If I go and try to calculate my density porosity in case of gas reservoir, here are my equations. I'm saying raw matrix, which is 2.71 minus raw bulk. If raw bulk is less, then the numerator becomes bigger. When the numerator becomes bigger, my density porosity will become even bigger. Okay, so the density porosity here in front of the sand will be much bigger. So let's look at this. It will be higher than 22.6. So this means my density porosity will be much higher. Look at this. The separation is still there, but it becomes big. So the notice that you will see if you are in a gas reservoir, that the separation still exists in the sandstone, but the separation becomes very big. Okay, so the separation was that small limited area, which is around 6 pu in the normal oil, but it becomes much bigger in case if you have gas. So if you have gas in sandstone reservoir, you will see the separation between the neutron density are really big. Okay, also you will see here, if we calculate the porosity of the limestone full of gas, then the density porosity will be much higher than 20. So in this case, you will see also higher than 20 for the lime. Higher than 20 means the limestone scale, the limestone is not going to be overlaying anymore. Even the limestone will actually have separation, but that separation is due to gas. So the separation is due to gas, becomes bigger. Okay, if I go for the dolomite and I do the same, the porosity will be higher than 12.5. So that will be the new one higher than 12.5. So you can see here, the separation becomes bigger. Okay, so that's the way that you will see the gas effect. Any separation you will see there becomes bigger, except for the separation of the dolomite becomes smaller. So the separation in case of gas in the dolomite, okay, becomes a little bit smaller. Why? Because actually it increases the porosity, so you can see the density porosity increasing, going to the increased number of 20, so it's getting closer, and also the neutron will be decreasing as well. So as you can see here, the gas effect will make the separation even more. Even the two that you were overlaying, which is the limestone over limestone scale, they used to overlay. No, now they will also separate. So the effect of gas, or if you are dealing with gas-bearing reservoir, expect the neutron and the density will separate. You will see huge separation if your reservoir is sandstone. You will see a small separation if your reservoir is limestone. You will see even a smaller separation if your reservoir is dolomite. Okay, but you will see separation anyway. You are not expecting that the neutron and the density will separate in front of the limestone, because we said limestone on limestone scale, they should not separate. That's true if you have oil, but if you don't have oil, if you have gas, the gas effect will make a separation even in the limestone. Okay, right. How about the neutron density? How about the porosity? The porosity is still the average porosity. Remember, we said the neutron porosity is not the correct porosity. The density porosity is not the correct porosity. The correct porosity is the average neutron density porosity. The average neutron density porosity, even in the gas reservoir, is the correct porosity. So even if you see the more effect of the gas reservoir, you still have the average is the correct porosity. Okay, so identification of gas reservoirs. Gas zones are easily identified using combined neutron density logs. Very easy. Dense neutron and density logs are separated more in gas reservoir compared to oil, and the neutron density average porosity is still your right porosity even if the gas exists. Okay. I need to summarize this because it's very important. Here is the situation where you have oil. Here is the type of separation, very small separation. In the limestone for oil, they are overlaying. In the dolomite, they are also separated. Okay, if I look at the gas reservoirs now, what will happen here that this one will increase, okay, and you can see there, this one will also show separation, and this one will also show separation. So the gas will do separation, but it will increase separation for sand, increase separation for lime, and decrease separation for dolomite. Okay, so this is actually the major effects of gas reservoir. So to identify, say this is a gas zone, look at the separation. Separation will be huge in the sandstone, and it will be separation on limestone. You don't expect any separation between neutron density on limestone unless you have gas reservoir. So if you have a gas reservoir, you see the type of separation. Also, you see the separation in dolomite, but you may see the separation in dolomite shrinking a little bit. The reason that shrinks because the effect of gas on the dolomite. Okay, all right. Again, the right porosity is the average neutron density porosity as we defined it before. Right? Now, how can I identify salt and anhydrite from logs? Again, guys, you always learn this. You need to actually go to the basics of things to really help you identify things. Don't memorize what the tool will do or what the tool will have or what the tool will show. So just go and see what are the basics of the tool measurement. Let's just go and, for example, salt. Salt is halite. Salt is actually, we call it halite. So how the halite will react on the neutron and the density? Let's just go first of all and look, what is halite? Halite is NaCl, sodium chloride. Ask yourself a question now. Is there any hydrogen in here? The question is no. It doesn't have any hydrogen. So if it doesn't have any hydrogen, what the neutron tool will do? Neutron tool is not going to find any hydrogen. If it didn't find any hydrogen, it will give you zero porosity. It's as simple as such. So you don't try to memorize things. Understand what are the basics of all these tools. The basic is halite is NaCl. The neutron tool, when it sees halite, it doesn't see any hydrogen. Since the neutron tool is not seeing any hydrogen, it's not going to give you any porosity. As simple as such. So in front of halite, it will give you zero porosity. Okay. So this is the first thing. So first of all, not radioactive. So the gamma ray is not going to read any high gamma ray. This is one thing. Second, it doesn't have any hydrogen. So in this case, the neutron will give you zero. How about the density? Density of halite is 2.13. So I will see also low density. So I will see zero porosity on the neutron. I will see low density on the density. I will see low gamma ray. Okay. So in this case, how about the resistivity? And the resistivity will read low or high. Okay. First of all, salt, is this salt actually dissolved in water? No. It's actually a salt bed. Salt bed is very resistive. Somebody say, oh, salt is actually conductive. No, salt water is conductive. But salt itself is not. The salt bed itself, there is no water in there. Salt water is the conductive one, not the salt. Salt is not conductive. Salt is very resistive. You cannot actually pass any current through salt bed. Okay, but if you put the salt in water, it makes water more conductive. So the salt water is the conductive. And some people actually have this mysterious thing in their minds. No, salt is not conductive. Salt water is conductive. Okay, so but salt is very, very resistant. Salt will be very, very resistant because there has no water in there. So salt is not, it's not NaCl solution, salt water, it's salt bed. Salt bed is very, very resistant. Let's just take an example here. Here is a log, for example. If I look at the gamma ray, it is very low gamma ray, as you can see there. Okay. And my density here is reading low. This is the 1.95. It's reading very low. My neutron is reading zero. Okay, here is the zero. So my neutron is reading zero. My density is reading low. My gamma ray is reading low. My resistivity is reading high. Okay, so these are the cases now. my neutron is reading 0, my density is reading low, my gamma ray is reading low, my resistivity is reading high. That's a typical response of any salt zone. So here is my neutrons reading 0, here is my density is reading low, here is my resistivity is reading high, here is my gamma ray is reading low. The 4 components we just talked about, these 4 signatures, if you see the 4 signatures at the same time, all combined in one of the sections of your log, you need to mark this section as salt section. Low gamma ray, low density, 0 neutron, high resistivity, that's a salt halite section. Okay, so the halite is very easy to find out by just knowing the properties of whatever you look at and how your tools are measuring. What are these tools measuring? So in this case, you can easily find this out. You don't have to memorize or keep in mind or whatever. No, it's just knowing the responses of your tools will help you out. Okay? For the anhydrite on neutron density, we need to go back and see what is anhydrite. Anhydrite is calcium sulfate, CaSO4, calcium sulfate. Does it have any potassium, thorium, or uranium? No, so it does not have gamma ray. It doesn't have any hydrogen. No, it does not have hydrogen. So if it doesn't have hydrogen, it will read 0 neutron. It's very simple. Neutron reflects hydrogen. So if it doesn't have hydrogen, it gives you zero porosity. Also, it doesn't have any potassium, thorium, or uranium to give you gamma ray. Okay. How about the density? Density is very high. So the difference here. So anhydrite will have very low gamma ray. Anhydrite will have 0 porosity. Similar to what? Similar to halite. But the halite density is very low, the 2.3. The density here for anhydrite is very high. So the difference between halite and anhydrite is mainly in the density. The other 3 are the same. You will see low gamma ray, you will see 0 porosity, and also you see very high resistivity because there is not really any water here in the CaSO4 to make the resistivity reading low. Okay? There is nothing there but calcium sulfate. So in this case, how about the resistivity? It's also no water. It will give you a very high resistivity. If I go to the same log, okay, and that's in the Gulf of Suez in Egypt. We go to the same log, the second section. Look at this section. Porosity is very low, okay, similar to the porosity of the salt. Okay, so it's very low porosity. Well, look at the density. It's very high. Look at the density here. Very low density. Look at here, very high density. So the density is very high. The neutron is reading 0. The resistivity is reading very high. The gamma ray is reading low. So it has low gamma ray. It has 0 porosity. It has high resistivity. The only difference from this and the halite is the density here is reading low and the density here is reading high. So once you look at this, this is your low gamma ray, similar to this. But instead of low density, it will be high density. 0 neutron, high resistivity, high resistivity. So what is the difference between halite beds and anhydrite beds? The main difference is the density. Density in halite will read low because the density of halite is low. Density in anhydrite will read high because the density of anhydrite is very high. So this is an anhydrite bed and this is the halite bed. So it's very straightforward by just understanding what are the tools measured and what is the property of the thing that you're looking at. Look at the property and use the basic understanding of your logs. With every log looks at thing. The neutron log looks at hydrogen. Density looks at density. Resistivity looks at is it conductive? And the conductivity happens with having by either any metallic components or any hydrogen. Okay. So in this case, the conductivity of the water components and the metallic components. You don't see this in any one of these two, neither the halite nor the anhydrite. That's why the resistivity has to be high. If you look at the rock itself, does it have potassium, thorium, and uranium? No, it doesn't. So in this case, why it should read a high gamma ray? There is no reason for it to read a high gamma ray. That's why they read low gamma ray. Okay? So identification of anything, guys, just look at what are you looking for, what are you looking at, and then decide what are the components of all these minerals and what every tool will react. Because every tool will react to something else, something specific in the composition of your rock. Okay, so this is actually the first two things, which is identification of the, or at least the evaluation of the gas-bearing reservoirs, how the neutron density will react to this, and we talked about the separation. Then the identification of salt beds and anhydrite beds as well. Now, many of you actually talked about the variogram processing. Okay, variogram processing. Let me remind you, at least, or warn you a little bit, because it's a very tedious process. I will go through it and try to make it easy on you guys how to do it, because variogram, as I said, is not as easy as a histogram. But let me start. What is a variogram? Variogram is mainly trying to do some statistical evaluation of data based on the spacing between wells. When we talked about the histogramming before, histogram does not take into consideration the well spacing. Histogramming I can do for a single well, okay, or I can look at the variation across a well, but without including the spacing between wells. And that puts a drawback on using the histogram for characterization of multi-wells. We need to find a way to look at how these wells are characterized together as a function of how far from each other they are. Okay, so the variogram will give you this. So the variogram provides quantifications of the variations based on distances between wells. Okay, all right. So for example, let's just take a reservoir. Here is a reservoir. All right, and for the first one, here is our area. My area will be divided by x-axis and y-axis, defined by x-axis and y-axis. Each well will has an x location and y location. Okay, and also there is the z-axis where this is the depth. So every well will have a location on the xy plane, and also will have measurements on the z, which is the depth axis. Okay? And let's assume that here is the layer that you will actually interested in. Here is your reservoir, and your reservoir I'm interested in, for example, the variation of porosity across my field. I need to look at variation of porosity across my field. So here is my reservoir, here is my target, and I need to look how the porosity is varying across my field based on the distances between the wells. Okay. So let's just first of all, let's assume this here is my first well. Here is well number one. Well number one penetrated the reservoir, and here is my reservoir section, and here is my XY point. So this well is drilled in X1, Y1. So I actually decided the location of my well on the XY plane. So I have X1 and Y1 for the location. And also, I actually try to calculate the average porosity using histogram for a single well. So from the single well, I can put a histogram here, and I calculate my average porosity. I call it Phi1 for well number one. Okay, so I will use the histogram in every single well, and I get the average porosity using the histogram for this well. That doesn't, I don't need to go for x1 and y1. There is no, it is only in the z direction. So in the z direction, I will calculate my average porosity using the histogram. Okay, so I did this for the first one. Then we decided to drill a second one. Second well would be in a certain location, x2 and y2. So the second well is in a different location, penetrated my reservoir, and also I measured the porosity in the section that the second well actually intersected in my reservoir. And it gave me an average of Phi2. So the average of porosity in the first well is Phi1, average porosity in the second well is Phi2. Remember, these two wells has a certain spacing. So there is a spacing between the two wells. I can actually calculate the spacing. If I have x1 and y1, and I have x2 and y2, then I can find the spacing between these two wells, which is the square root of x1 minus x2 squared plus y1 minus y2 squared. So this is actually the distance d12, means the distance between well 1 and well 2. So d12 is the distance between the first well, well 1, and well 2, and I can calculate the distance between any two wells. Dij, whatever well I and well j, is actually x1 here minus x2 squared plus y1 minus y2 squared, or to make it a generic, xi minus xj squared plus yi minus yj squared. So I can actually get the distance. So now I have the distance between the two wells, and I have the average of my porosity for every well by itself using the histogramming for the first well and the histogramming for the second well. Now, let's assume I drill the third well. The third well now will have a location X3 and Y3. Now, it also penetrated my reservoir, and I will be able to calculate with the histogramming my average porosity P3 of the third well. So now I have three wells. What are the combination of distances in this case? First of all, I got the distance between x1, y1 and x2, y2. I already have this two, and then I have to go x1, y1 with the x3. So the distance between x1 or well 1 and well 3, and the distance between well 2 and well 3. So now I will have three distances, all right? So the second distance is the distance between 1 and 3, d13. I will go, I use this equation, dij, to calculate the distance d13, will be the square root of x1 minus x3 squared plus y1 minus y3 squared. So I got the distance between these two wells. Again, there is another distance between well 2 and well 3. I will call it d23. d23 is the distance between 2 and 3, which is simply x2 minus x3 squared plus y2 minus y3 squared, and I take the square root. So I can actually decide the distances between all wells, okay? And also I use the histogramming to get the average porosity for well 3, average porosity for well 1, average porosity for well 2. So now I will build a certain table. That table goes into what is the distances between each well, each two wells, and also what is the average porosity for each well. Okay, so I'm collecting data now. All right, then I will say, okay, there is something we will define called the variance or gamma. What is the gamma? Well, Phi1 is different by Phi2. For example, the average porosity here is 20 Pu, but the average porosity here is 18. All right, the average porosity here is 17. So what you do is, once you calculated D12, which is the distance between 1 and 2, you actually get the difference between porosity 1 and porosity 2. So you say Phi1 minus Phi2. Here is the difference, all right? And you make it square, because we don't want to, if Phi1 and Phi2 or Phi2 minus Phi1, it doesn't matter. If you make it square, you will actually take care of the negative sign. So it will be Phi1 minus Phi2 square. So I got the distance D12 and the variance of the porosity between Phi1 and Phi2. Then I calculate the distance D13 and I get the variance between 1 and 3. Phi1 minus Phi3 squared. Then I get the distance between 2 and 3, which is D23, and the variance between Phi2 and Phi3, which is Phi2 minus Phi3 squared. You add all these variances, you divide them by the number of wells, and you take the square root. We call this a variance. So here is actually the variance gamma, which is a function. You get the differences, how the well is different from that well. You go for Phi2 minus Phi1 squared, Phi2 minus Phi3 squared, Phi1 minus Phi3 squared, and I add them up. Then I take the square root of all and I divide them by the number of wells. So you add up the variances, you sum them up, you divide them by the number of wells, and you take the square root. We call this variance. Okay, right. That's a very simple example. Actually, in reality, what we usually do is, here is how we do. Phi1 and Phi2, we get the difference squared. Phi1 and Phi3, you get the difference squared. Phi2 and Phi3, you get the difference squared. You sum all the differences. You divide them by the number of wells, and you take the square root. It gives you the gamma. Okay. Right. It gets more complicated now if you go to reality. Reality is, okay, once you finish this, you go for the distances versus the variance. So now we have distances D1 to D1, D1, 3, D2, 3, and so on. You get the distances versus the variance. So you calculated the first distance versus variance, second distance versus the variance, and so on. You plot them distance versus variance, and you get the relationship. Now, as you can see, these three wells, okay, as an example, they are in correlation. You can see it's actually increasing. How at this well? It's off correlation. So we call This distance is a correlation exists between this well and this well is off correlation. So I can look statistically where is the distance that's off correlation different than the other part of the reservoir, and where are the reservoirs that are correlated as a function of distance to variance or variation. That's why we call it variogram, the variance as a function of distance. Okay. Okay. Let's just do this in real example. Here is a real example. I have actually multiple wells here. How many wells? I have about 16 wells. So the number of wells, actually I have 16 wells. So the first step is to list all wells location and the property of interest. Okay. For example, I have well 1, 2, 3 up to 16. Every well has an X and Y. So this is the X for well 1 and Y for well 1, X for well 2 and Y for well 2. And I'm interested in porosity. So this is the porosity of well 1, 2, 3, and so on up to 12. So I make a list of all the data I have. Well 1, X and Y, and porosity. You can do that for porosity, clay volume, water saturation, permeability, whatever you like. You can do variogram for any property that you want to do for. So the wells, X location, Y location, and the property. Okay? So this is the first thing you need to do, is to list down all of these wells. Okay? Then you create a table of all possible well distances. It means the well distance is xi minus xj squared plus yi minus yj squared. That will take the square root. These are the distances. No repetition. It means the distance between 1 and 2 is the same as the distance between 2 and 1. So you don't go and calculate distance between 1 and 2. Then you calculate it again as 2 and 1. It doesn't make any sense because the distance between 1 and 2 is the same as 2 and 1. Okay, so it's either you use 1 and 2 or you use 2 and 1. Okay, so that's why we call it no repetition. You don't repeat it. Okay. Second, meaning the distance ij is the same distance ji. Okay. Mathematically, how many combinations you will have? Okay. It's actually mathematically it's n plus n times n minus 1 divided by 2. What is n? N is the number of wells. As I told you guys from the beginning, it's a very tedious process. So because it's a lot of combinations that you need to look at. N is the number of wells. So number of wells is 16. Then 16 times n minus 1, which is 15. 16 minus 1 divided by 2. It gives you the total total number of combinations that you may have between all the 16 wells or any number of wells. So in this case, the number of wells is 16. So how many combinations between distances I have in these 16 wells? Sure, look at this. Only 16 wells. Sometimes we have 300, 400 wells. Look at how many combinations that you will have, thousands. Okay, so it's a number of wells here is 16. How many combination of distances I will get between the 16 wells? First of all, it's actually 16 plus 16 times 15 is n times n minus 1 divided by 2. You have 136 combination of distances and variances. Okay, everybody understand that? So in this case, you will have a lot of correlation that you need to build tables for, and you see the variability of it. As you can see, is much harder than what the histogram is all about. Okay, so you look at the combination of distances and the variance between all these distances. Actually, the way we do it is to build a table. A table has X, which is 1, 2, 3, 4 up to 16, and you can do that on Excel, and also the Y 1, 2 up to 16. Okay. Here is the wells that well by itself, 1 and 1. 1 and 1, the distance is 0. So it means there is no, these are the wells by itself. Then I have well 1 with well 2. We call it D1, 2. Well 1 with well 3. So D3, 1, D3, 2. Well number 4 was 1, D4, 1. Well number 4 was 2, well 4, 2. I don't fill the other part because it's going to be 4, 3, 2 is the same as 4, 2, 3. So it doesn't make any sense to fill the upper part. We only fill all the possible combinations between wells. So this, for example, here, well 6. Well 6 will have a distance between 6 and 1, distance between 6 and 2, distance between 6 and 3, 6 and 4, 6 and 5. And you go to well 7, 7, 1, 7, 2, 7, 3, 7, 4, 7, 5, 7, 6, and so on. Okay? Then you fill this. If you do this in Excel, it will be an easy thing. But this is how we fill it. If I do it on Excel, here are all possible distances based on the well locations I have. As you can see, huge type of calculations that you need to decide the 136 spacing between the 16 wells. So the 16 wells created 136 spacing. Okay, all right, all right. Once you did this, then you have to do what? You have to list all possible combinations in tables. For example, I can see here well one and the order is well 1 and well 2, well 1 and well 2, well 3 and well 1, well 4 and well 1, and so on, until you go for well 16 and well 1. Then you have to well 1 to well 2 and well 1 and well 2 and well 2 and so on. So you have all these possible distances between wells. Okay. For example, here is the possible distances for well 1. Here is possible distance for well 2, and so on. Possible distances for well 3. So you take it a well by well. So well 1 will have a distance between 1 and 2, 1 and 3, 1 and 4, 1 and 5, and you list the distances. Then well 2 will be 2 and 3, 2 and 4, 2 and 5, and you list all the distances. Well 3 here, 3 and 2, 3 and 3, 3 and 4, 3 and 5, and so on. Okay, so you will have all these possible combination of distances between wells. Okay, so you list them all. Okay, then arrange them. Arrange the distances from low to high. For example, here are the distances of 0 means the well on itself. Then distances will increase here. This is 200, this is 205, 281, 300, 370. You can do that easy again on Excel, because Excel can arrange things ascending or descending. Okay, so you arrange all the distances from the 0 all the way to the maximum distance that you have. Once you do this, here is the 0 distances, here is distances increasing this way. Okay, so here is 0 distance means the well on itself. So the well will have its own variances with itself. Okay, then once you do this, so you have now you decided what is the distances between wells. Then you go do whatever you used to do with the histogram, which is the range of the data. What is the range of the data? The minimum value of distance and the maximum value of this. Minimum value of distance will be 0. Here is the minimum value, and here is the maximum value. So we have the minimum value and the maximum value. We call this range. So the range will be the maximum value we found from the data is 2100 minus the minimum value is 0, so the range is 2100. Now we divide the range into bins. Remember that from the histogram. We divide the range. Now, what is the range? Range is the distances between wells. That's how now we combine the distances with the histogramming. So the histogram now will take care of the distances, and we see the variances between the different wells. So here is the number of bins, let's say 10 bins, okay? And you decide on the range. How can I get the range? You divide the range on the number of bins that you decided. Then each bin would be 233 distances, or 233 meter, or whatever the distance that you're measuring. Okay. Then you list all these ranges in bins, like with exactly what we do in the histogram. So look at here. Here is bin number 1, bin number 2, up to bin number 10, because you decided that the number of bins are 10. Here are the distances of the bins, and here are the range of each bin. Okay. Remember, when we take actually the range, we decide on what is each one of these bins will be. Here is bin number 1, bin number 2, bin number 3, and so on. So actually, as we used to do for the histogramming, and also we decide for the midpoint of each one of them. All right. So we have actually defined the bin and the middle of each bin. All right. Once you do that, I know it's, as I told you, it's a very tedious process, but it's simply because you can see a lot of calculations here, and I'm just taking a very simple example. A field that has 16 wells. Now, if you have 300 wells, imagine how many calculations you will do. Softwares actually do that for you, but that's how the softwares work. So in case the software does not give you the proper distribution and you feel something is wrong, so you know exactly what went wrong with the softwares, and you go back and you look at your data one more time. Okay. So let's just continue on this. You actually decided on the bins, and here you have each bin minimum and maximum. and also the middle of each bin. Okay. Once you decided on the start and the end of each bin, you look at the number of wells in each bin. Here, number of wells here is 16 in the bin number 1. Number of wells here is 7, 25, 26, 23, 18, and so on. So you have 7 wells that actually lies between these two ranges. So the distance 116 to 350, I have 7 wells that has these distances. I have 25 wells that has distances from 350 to 580. And I have 26 wells from 580 to 816, and so on. So I now decided number of wells that goes within this range of distances. Okay? Once you do this, then you calculate the variance now. Variance is phi I minus phi j squared. Remember porosity here. Porosity from well 1 minus porosity well 2 squared, and you add them up, and you divide them on the number of wells. Then you take the square root to get the variance. Once you got the porosity and the distances, you calculate the variance for every single group of data, because the variance here is 0 between themselves. And if you go to the second group, you calculate the variance here between phi1 minus phi2, phi3 minus phi4, 5 minus 6, 6 minus 7, and so on. You sum them up, you square them, you sum them up, and you divide them by the number of wells, you get the variance. If you do this, for example, here is 12.7 minus 15.8 squared. 7.6 minus 15.2 squared, 11.9 minus 7.6 squared, and you sum them all up, and then you take the square root of sum divided by the number of wells, which is 7 wells in this case. Okay, so you get the variance. You repeat this for all of them. Okay, here is another example of other group of data where you calculate also the variance as 14.05. Okay, then you finish all bins, and then you list them. Here is the distance versus the variance. Then you start plotting distance versus variance. Here is your distance, and here is your variance, and you can see all these are in correlation, and these are off correlations. Okay, so wells in correlation, wells are off correlation, as we saw in the previous example. And then you say this is wells off correlation, these are wells in correlation. Okay, so only wells with those distances less than 1400 feet are wells in correlation. So now we can see the wells that has correlation together has to be within certain distances, and the other exceeding these distances will be off correlation. But you cannot actually find this from any type of histogram. Okay, as I said, this is a tedious process, but the whole idea is to look at to try to combine all possible distances between wells and the variation between the parameters between wells, and you start build the correlation between distance and the variance of the parameters, and that's what we call the variogram as a function of distance. Okay, right? Actually, I'm done with these 3 components that we started saying that we will cover this, and I'm now ready for any other questions that or any comments even of what we covered so far. If anybody has anything that's not clear, or if I have any different questions that I can answer in the upcoming few minutes. All right. I think.
Thank you, Dr. Moustafa. Yes. Thank you, Dr. Moustafa. As usual, the session was very informative and clear. We got some other questions. I will pick some of them to answer.
Please go ahead.
Someone is asking, I don't understand what are the difference between clastics and carbonates. For example, I see limestone in both of them. So can you explain?
Okay. Actually, when you say clastics and carbonates, okay, that's a depositional environment. Okay. Clastics is mainly in sandstone, which is silicon dioxide, SiO2. Okay, so silicon dioxide represents clastics. Clastics can vary in grain sizes. For example, you can say coarse grains and fine grains. When the clastic becomes fine grains, we call it siltstone. So we have sandstone and we have siltstone. Sometimes, as you said, you can find limestone within clastics, but that's not actually takes the clastic to be carbonates. No, we call this calcareous sand. Okay, so we have actually definitions for this. There is nothing sharp in nature. Okay, so you can actually find limestone in clastics for sure, but we don't say this is a limestone formation. We call this calcareous sand. It means sand that has some calcite in it. Calcite is carbonate. Okay, You can also find some dolomite in sand. Yes, you can. You can find some sand in carbonates. Yes, you can. Okay. But when you say that the majority, for example, if I have 80% of my rock is sand and 20% is calcite, we don't call this carbonates because it's dominant by clastics. Okay. Clastics is a sandstone. It's a silicon dioxide texture. It's grain. Okay. But if I have 80% limestone and 20% sand, we don't call this sandstone. We call this limestone because it's the majority of it. So the existence of some other lithology included in certain majority of a lithology, that doesn't change the name. Okay. So it's to be more careful. If you really work professionally, you say this is calcareous sand. Okay. Or we call this dolomitic limestone. Dolomitic limestone, it means it's a limestone that has dolomite in it. So there is nothing called clear limestone, for example. In some reservoirs there are clear limestone, but some other limestone you can see dolomite built in the limestone. So variation, and there are so many processes actually, or processes to do this. So you're right. But when you start naming a name, aim it to the majority. If you have 80% sand, then it's a sandstone, and has 20% calcite. Yes, we call it calcareous sand. Okay. If you have limestone that has dolomite, it's called dolomitic lime. Okay. So do we have this type of naming? But you name it on the majority of the lithology that you have. Okay. Yes, ma'am.
Okay. What are the required parameters to build a basic reservoir characterization model, and how?
Okay. That's a very long question. Well, first of all, let's forget about the parameters first. I think you need to get yourself strong in how you look at logs first. Okay. And you need to get yourself strong. If you are not very strong in geology, get in a very good contact with geologists. Okay. You cannot do characterization without having a full understanding of the environmental deposition, how this reservoir is built, okay, the environment of it, okay. Being in, I don't want to go into details in geology because I don't want to complicate things here, but at least you need to do the environmental deposition, okay. What type of reservoir you're dealing with. You need to go into depth with the composition of your rock, understand with the geologist what is the composition of your rock. You need to understand the response of your logs, because actually the input that comes from the geologist will be in a limited time. Now, the majority of data that you will use for the characterization is logging, because we do logging in every single well. Okay, you don't do coring in every single well, but we do logging in every single well. So you will learn the geology and the deposition and the properties of your rock from 1, 2, or 3 cored wells. But the majority of your work is to look at logs. So you need to understand the logging response very clearly. You're not memorizing it. You really understand it very well, the response of your log. Second thing is you need to tie in between your understanding of logs, your interpretation of logs, and what the core is telling you. That we call integration between core and logging. That step needs to be done before you even start talking about characterization. So the geological input, the depositional input, the logging understanding, the integration between logging and coring, these are very important factors that you need to start really teaching yourself or training yourself on how to make this, and you have to get yourself very strong in this. After that, you need to look at all the wells. You need to build your understanding of how to look at multi-wells data, okay? How to do multi-wells processing, because you cannot actually process every well separate. And when you choose parameters for your reservoir, you don't choose it on a single well by single well. You cannot do that. You have to learn how to choose multi-wells parameters. Okay, when you look at the statistical variation, you don't do this on a single well statistical variation. You have to look at multi-wells. If you go for any softwares for characterization, you see two options: multi-well, single well option, and multi-well options. Okay, So you have to teach yourself first of all the skills to do full analysis for a single well, then the skills of combining wells together. There are so many steps, and believe it or not, you will gain this through the years. Nobody will teach you this or the steps. You will learn one step at a time, and then you would see yourself later on that you started to grasp everything, and you see how all these pieces of the puzzle are connected together to be a good characterization engineer. Okay.
Okay, next question is what is the difference between core helium porosity and core fluid porosity?
Okay. Well, there are two ways actually of measuring porosity in the lab. Okay. One of them is to heat the core and to collect the fluids that come out of the core. Okay. For example, I have a sample of a core here, and now to get the fluids out of it, I will not do that by pressure. It's not going to work. Okay. So what we do, we heat this piece of rock, and we extract the fluid that comes out of the heating because it will evaporate, and from the evaporization we can collect them after that by condensing. To evaporate and condense to get the fluid. That's how we extract fluids. We call it the fluid porosity. Okay, this is not really a good porosity measurement. It always underestimates porosity because when the plug actually comes to the surface, the plug was at the bottom at 10,000 feet, 15,000 feet. It's under pressure. Once you actually take it to the surface, if you are not preserving it properly, the fluids will leak out. Okay, so you will lose some of the fluids. So normally you see that the liquid porosity is less than reality. Okay? But once you actually cleaned it, and now there is nothing inside it, now we can use the helium. Helium will be measuring your porosity, and the helium has a very important advantage. It's not a liquid. Helium is a gas. So helium will actually go and inside any type of pore, even the small ones. Okay, so helium will go through the small ones, and it will give you exactly the total porosity, or let's call it effective porosity in this case. So it will give you the porosity because the gas will fill the whole rock, even the small pores. If you try to do this by fluid injection, you're not gonna succeed. So the fluid porosity or the liquid porosity is the porosity that we measure by extracting the fluids from the core. And this is normally less than the helium porosity. Okay, helium porosity is after you clean the plug, you actually use the helium as a measuring gas for your porosity. Okay, normally helium porosity is higher than the liquid porosity, and the helium porosity is the most appropriate one in this case.
Next question. Do I histogramming all the gross zone data or only the net pay section?
You only do the net pay. At anything actually, when you even do calculating effective porosity, I saw some students, that happens also in where I teach. Some of the students, when they pick up, for example, the gamma maximum and gamma minimum for clay, they go from top to bottom for the well. That's not right. Okay, you need to concentrate on your zone of interest. Okay, and also just give yourself plus or minus whatever 100 feet or so above. If your top of the reservoir is, let's say, 10,000, give yourself 100 feet above it and 100 feet below it. So you put your reservoir in this sandwich and try to pick the parameters of your reservoir, because if you don't do that, you will add some junk data to your reservoir that doesn't belong to your reservoir. Okay, make sure that you do this around your reservoir, and work with your geologist to make sure that you're not adding junk to the zone that you are doing you're doing the calculations on. So you need to be very careful when you do that.
And now this is the last question. Someone is asking, so the negative separation isn't the best way to determine gas-bearing reservoir, am I right?
What do you mean by negative separation? It's not a negative separation. The more separation you have, okay, the neutron density will separate more. I'm not saying negative. Okay, for example, let me give you, if we wanna do this, I don't wanna say numbers because some people actually stick to these numbers, which they may differ from one place to another. But let me give you at least a rule of thumb. If you are in a sandstone formation and you are in an oil reservoir, expect your separation between Newton density will be between a maximum of 6 PU, 6 porosity units, difference between Newton and density. If you see more than this, okay, try to think of, do I have a reservoir under bubble point? So if I see, so for example, 7 or 8, that may indicate that your reservoir is under bubble point and gas has started to build up. If I see 10, 12, 15 PU differences, you are in a gas-bearing reservoir. So the separation measured in porosity, so look at the reading of the Newton reading and the density, and try to subtract these two readings. If they are 6 PU or less, you are in an oil reservoir. If it's above 6 PU, say 7, 8, you are in a reservoir under a bubble point. If you are talking about 10, 12, 15, 15, then you are in a gas reservoir. Okay?
And that's a wrap. We would like to express our deepest gratitude to you, Dr. Moustafa, for the course. It was very informative and interesting. And as usual, please be informed that the lecture will be uploaded to PyPetro YouTube channel. And I would like to inform you all that there will be 3 timings for the final exam: 2 p.m. and 8 p.m. on Friday, and 2 a.m. on Saturday, all in Egypt time. So please choose one of the mentioned timings to solve your exam. Thank you all and stay safe.